Yeah. All right, well, I'll go ahead and get started. Thank you, everyone, for joining us. This is our first technical working group of the new year, so yay, yes. This is meeting number 14, and just to give you guys a bit. First of all, we're going to be covering a bit of news about the OpenEEmeter 4.0, which is the daily model. Then we're going to be doing a recap of the last meeting, followed by looking at some of the new models that we've been investigating, and finally diving in a little bit deeper into ElasticNet results. So, to start off with, the OpenEEmeter 4.0, or the daily model update, as we have been calling it. So first of all, as everyone knows, we have completed our model. Though if you are interested in the final model specification and results shown here, just very briefly, the title slide, the title page, as well as some of the primary results. There is a link here, but I don't think you'll be able to access that right now. So if you simply Google OpenEEmeter 4.0, then that should be the first thing that pops up, and you will be able to click the link to this PDF. For those of you who may be less familiar with...
We're losing you, Travis, here and there. I don't know if you want to maybe go on or without video.
Yeah. Yep, let me do that. For those of you that may not remember, the daily model was where we were really trying to dig in and reduce both seasonal bias as well as weekday weekend bias, which we accomplished quite well. In addition to that, we sped up the model quite a bit while keeping the 3.0 mode, so basically the same type of model that you would get in CalTrack 2.0. That is still available in OpenEEmeter 4.0, just in a 3.0 mode. And this is just a quick little graph that shows you that you basically get the same exact results. Now, there are a couple of things. You are not, or you are correct, Ethan. So CalTrack 2.0, 2.1 was supposed to be like the update of CalTrack, but we have since moved off of the versioning from talking about CalTrack because the versioning between CalTrack and OpenEEmeter did not match up. So since this is an OpenEEmeter working group, we have just decided to drop all of the 2.1 and so forth. So we're just referring to it by its OpenEEmeter version number. Work in progress. There is a lot that we are doing still on OpenEEmeter 4.0. Most of that is more on the back end of things, though, less so on the modeling, as the modeling is complete. What we're doing here is we're wanting to combine OpenEEmeter, EEweather, and other open source software into a single library. The reason we want to do this is because there's a lot of common functions, and if they're all just basically duplicated in these libraries, and that means that every time that we want to update one of these common functions, we have to update it in every single library, which one is just a little bit of too much overhead, but two, it also adds in the possibility of doing it incorrectly or skipping one, in which case that would be problematic. The other reason is that these libraries are already dependent. For example, OpenEEmeter expects that you are going to be using EEweather in order to get your temperature data. So it doesn't even really make sense that they're separate. They should basically just be modules within the same library.
Can I ask?
Go ahead.
Is it still going to be possible to call the lower level APIs with non-EEweather data? And I'm less concerned about the weather actuals than the typical TMY data.
Yes, you will still be able to provide your own temperature data. It's just that what we're trying to do is make it so that the flow, if you choose to use all of these together, that they all flow from one to the other much more easily than they do currently.
I support that. Thanks for clarifying.
Of course. The other thing that we're looking at doing is deprecating the Caltrack specifications. That is not to say that these things are going to completely disappear, but what we want to do is we want to move the model documentation to the repository itself, so that we will have basically a directory inside of the repository that will contain, for example, the previous model specification PDF that I just linked will be in there. We want to keep everything in one place. The other thing that we're wanting to do is we're wanting to move data sufficiency from a list of requirements that you must follow in order to comply with the Caltrack specifications to something that is written into code, something that is going to be much easier for a person to not make a mistake and include data that they should not be. And on top of that, we want to do some additional API changes, still all kind of in the same vein, where what we want to do is make everything easier to use. And so what we're looking to do is what works now, but we're also wanting to make sure that the choices that we're making with the API will continue to work in the future. For example, the hourly model. And the overall guiding idea here is basically we want global simplicity, and we are willing to accept that we're going to have some local complexity in order to be able to manage this. What I mean by this is globally, we wanted the calls to be basically the same. Whether you're going to call the hourly model, the daily model, the billing model, we want the calls to be the same. Now, they might have different specifications and they might have different options. So there will be some local complexity where you may have to, if you want to put in your own options, those will be different. And that's what I mean by the local complexity. But overall, we want this to be much more seamless. Now, we are taking inspiration from sklearn. And now what I'm showing here on the left is just an example of how to call some of sklearn's clustering API. And on the right, their regression API. These are very different operations. But if you look a little bit lower where I'm actually calling these things, this is where I'm just defining which methods I'm calling. But where I'm actually calling them to use them, it is .fit and .predict, where I am passing in some labels, and here I'm telling it, here's some new things. What are the labels? Or sorry, the top one is here's some data points. The bottom one is here's some new data points. Give me the labels. If we compare that to regression, which is a completely different operation, it's still very, very similar, where it's still a .fit where you are passing X and Y data, and then the .predict is exactly the same with X new. And they're managed to do this with even more complex things than what I'm showing here. And so I want to take inspiration from sklearn and make it so that our models are much more easily used. Now, overall, the goal here is ease of use for the user as well as developers. So for Caltrack 2.0 or OpenEEmeter 3.0, I should be consistent, and I was not even consistent here, Ethan. Most of the steps that people use is from tutorials, and we know this from the user feedback that we get. So you look at the tutorials, you see how to run the model, you just copy the steps and paste in your data where appropriate. That's kind of redundant and unnecessary. What we could do instead is we could just use simple function calls where we instantiate a class, call a fit, and predict just like sklearn does. Now, using these same tutorials, there are different processes for daily and hourly modeling. Whereas in this new architecture, it would still be the same exact function call regardless of what the model is. In Caltrack 2.0 or OpenEEmeter 3.0, the user sets the options in the sub-functions. Again, this is an area where it makes it so that the configuration that you're using is not always straightforward, and where you are declaring these things isn't always readily apparent. Whereas with OpenEEmeter 4.0, we want to just have a configuration class with that automatically has sensible defaults set and that you can choose to override if you choose. Lastly, in OpenEEmeter 3.0, there are intermediate information from subfunctions. So you're calling these various functions, which are the steps, and you get some information there. You could see this as being very valuable. And if you do, well, then I would assure you that we can still keep that intermediate information, except we could keep that within the class so that rather than having to call these functions sequentially in order to get that information, you would be able to just directly call it from the class that you have instantiated. So I've covered a reasonable amount. Are there any questions or concerns so far? All right. So now I'm going to talk a little bit about some of the details of what I mean by these things and what it means in practice, because we have put some work into making these things reality, not just an idea. So this is an example of the daily and billing models. And I'm not going to go through all of the code here on the left, which is the OpenEEmeter 3.0. But basically, you have to set up your design matrix, call some more functions where you have to set the blackout dates and whatnot, and then you end up getting metered savings. What we propose that we do in the future is rather than having to set blackout dates and all of that, we will set it up so that you only pass the data that you are going to be using. So if you want to fit, which you do on the baseline period, then you will pass into a data baseline class, daily baseline data class, the meter data and the temperature data. And then you would do the same thing for the reporting data. And then for the model, you would instantiate the model class with a settings file. Here, I mentioned the defaults, and so it's actually unnecessary for me to include the settings equals none, but I went ahead and put that in just to give you an example of how if you did want to provide a settings file, this would be where you would do that. And then you simply call the .fit on the data class that you have created up here. This will be important, which I will explain here in just a little bit. This model class is now the fit model. So then you can call a .predict on your reporting data, where you would then get basically a copy of your reporting data plus the predictions that you are wanting. And from this, you'll be able to calculate your savings, though we're not explicitly making a function for that, as it depends on how you're choosing to do that, whether or not you're doing comparison groups or if you're just directly doing uncorrected savings. Now, similarly, for the billing model, here, again, you'll notice that this, if you just glance between the top and the bottom, not going through the code, it's different, even for daily and billing. And yet here on the right, nothing really changes. Instead, we simply call a different data class. It's the billing baseline data, and we call a different model. Everything else is exactly the same. And this should make it so that for those that are wanting to use these models in practice, it will be much, much easier, and you will need to know less about the inner workings of the code. This is even more substantial when we start talking about the existing hourly model. Now, in OpenEEmeter 4.0, we are not changing the hourly model. However, we are changing it so that if you want to access the hourly model in the same API structure as the daily and billing, you can do so. These are basically just wrappers around all of this code as a convenience. But you can see here where this really starts to be helpful, and that's when we're having to combine all of these different functions, whereas, again, same as before, this is just a simple matter of instantiating the class fit predict. They're all the same. Now, talking a little bit about the data class. So the data class is where we are going to be trying to enforce compliance, previously Caltrack compliance. And to do that, we add the data to the data class, and then that data class is the requirement to go into the models. This ensures that you have not bypassed a step with accidentally. There will be ways that you can override the various compliance checks, but instead of it being accidental, now it must be explicit. So inside of the data class, we will keep track of all of the violations or checks. And the way that this works in code is a little bit off here to the right, where we instantiate the baseline data class. These are going to be different depending on whether you're doing hourly, daily, or billing, but regardless, same structure. You give it the correct data. We're still debating about what the inputs and outputs here are going to look like, but largely that's just syntactic pixie dust. So we'll get these things sorted out by the final release. But ultimately what we want is something where you instantiate it, and then you will be able to just call a method from within this class, such as sufficiency warnings or critical sufficiency warnings. And that will return back something like this. For example, if you have a critical sufficiency warning, perhaps you had too many missing days of temperature data, then we'll provide information about that, what is required, what was actually presented. Same thing with the non-critical. And this is all going to be within the data class, but as I'm sure that most are familiar with, Caltrack compliance is not just about the data, it's also about model fits. And so what we want to do is this class will be passed forward, but that also means that the violations will be propagated to the model class, which means that if there is, for example, a CVR-MSE requirement, that will also be checked, and it will be able to be found within the model class in the same place that the data specifications will be able to be found. Are there any questions or concerns?
Hey, Travis, it's Ethan. Maybe you're getting to this, but is there a way to just override the default Caltrack criteria to do a run with different data sufficiency or model fit criteria?
We have not set up a way to override it in the sense that you can change the criteria. Now, if you wanted to do that, you could go ahead and inherit the class and change the things that you want to change. That's a bit more low level, but what we are doing is if you do not want to follow the Caltrack criteria, then we basically put in, there's two ways that we're going to handle this. Two trains of thought here. One is that the model would not proceed unless it passed the data compliance. And then there would be an override of ignore Caltrack compliance during the model fit step. The other is that we would always fit no matter what, and then it is up to the user to check whether or not there are any sufficiency warnings.
Okay. Yeah, I mean, the example are, some research project or something, and someone says, well, can we look at everything with an R squared better than 0.2? Obviously it's not for like program savings with Caltrack or anything like that, but there's still some kind of threshold. And I mean, that's basically what we've done with past versions of it, is run everything through with no rules and then filter stuff out at the end. But I didn't know if, as you were revamping this, if there was some way that you could like create a config file or something with the that abstracted out all the settings. The other thing that would be nice about exposing them a little bit more is that periodically someone asks me and I've forgotten like, oh, exactly what is the threshold there, and like reading through all the code is sort of a silly way to find it. I mean, I know it's in the methods docs and all that, but it would be kind of cool if it was like separated out into some little JSON file or something somewhere that was like very transparent about how that was separate from the code. Anyway, just some thoughts. I mean, this is all great and usable and functional, but that's my feedback.
I like the idea. My concern here is we're really wanting to make it so that if there are any changes to the criteria that it's, or to, if the criteria are to be ignored, then it really has to take some level of effort by the user. My concern with a config file that is easily changed would be, can it get changed and they simply forget to change it back, kind of thing. I'm not sure how to balance these. These are kind of competing goals.
Yeah. Sounds like this is a follow-up where we sort of think through what we might want to actually be able to support about this. But I mean, I think bottom line is, as long as there's a way to pass a flag through so that models, even on non-passing data sets and model fits, as long as it generates the outputs on all of them, there's always the fallback that you just run it with, you know, violations ignored, and then you can do custom filtering at the end. So that's an adequate workaround. I mean, these are usually research projects, right? Not program saving. So it's not pressing to do something sophisticated.
Right. Well, I think I propose that we continue on as is for now. But if you can come up with an idea that kind of bridges the gap between these two things, I'm always happy to entertain those and implement them.
Is the issue that we would by default or just altogether not be calculating the models for any meter that runs into one of the Caltracs or one of the OpenEEmeter specified disqualification criteria?
I cannot remember the choice that Jason and I came to. Is Jason on the call?
Yeah, Amir, can you repeat that?
Yeah, Jason, we're asking about, oh, Travis, please go ahead. Yeah.
Did we make the choice to, if there is a data sufficiency issue, that we cancel the fit, or did we set it so that it will fit no matter what?
I think we were still going back and forth on that. One was either going to be, so either way we would have a parameter that allows you to force it. But we were deciding on whether it would be, whether the pattern would be a try except around the model fit, or if it would be on the predict, or potentially both. But either way, you'll be able to override it. So we'll just have to document that.
Yeah.
Okay, so it sounds like Ethan, does that assuage your concern that regardless of the specific functionality, the user would be able to override that, or would be able to still create the models for customers that wouldn't have sufficient baseline data, for example, those kind of things?
Yeah, that sounds fine. I mean, it would be cool if you could tune it out so it had your specific rules, but this is totally functional, and I'll check the docs when it comes out to see how to you know, run it in no holds barred mode and go from there.
Yeah, sounds good. If there's other like aspects of that we want to discuss, we definitely should. We can come back to it. I am curious, based on some of these changes that Travis is talking about with respect to taking inspiration from scikit-learn, if others on the call have used scikit-learn or familiar with those constructs, and if there's any feedback on you know, whether or not things we should pay attention to or watch out for, or if it's just kind of all together. I mean, in our minds, it's a way to gain much more consistency and standardization over how you call any of these models, and to make sure that the defaults are essentially very sensible. You know, a lot of stuff that people really don't need to touch very often and are more for expert users don't necessarily need to, you know, complicate the function calls themselves, or, you know, cause you to have to call multiple functions to get the same, you know, result. So I'm curious if there's any feedback on these changes from the broader group, especially from folks that might have used scikit-learn in the past.
Yeah, I'll just speaking of this is Will. Very pleased to see that y'all are moving to the .fit, .transform, .predict sort of API standard within scikit-learn. That'll make it a lot easier to plug this in where we might have been using something else in the past.
Thanks, Will.
Hey, this is Mustafa. I use Light GBM, and I was wondering if I completely in line with the Eton kind of proposal. So for example, for the Light GBM, there are plenty of options that's set to be default, and there is a possibility for the user to change them based on the requirement. So kind of my thought here is, if there is a possibility to consider, for example, those threshold for the data sufficiency as a default, and then there is a possibility for the user to change them on a case-by-case basis. Let's say, for example, we are looking at the modeling and the data sufficiency required 90% per month. Data is available, but there is no seasonality in one case. So, for example, the user can run the model with just 2 months of the data with less than 90%, let's say 20% of the data available, as long as they can set those threshold or lower those threshold.
So yes, you would still be able to do that. You would just basically ignore all the issues. Now, the way that we have things set up right now is we are providing more information than just it failed because of this, and then the entire data class is basically marked as insufficient. We're not doing that. What we're doing is we are going through every single check and marking the ones that do not pass, which means that if you wanted to, you could go through and you could check these yourself to make sure that, oh, well, I'm going to ignore all of the data sufficiency, for example, the 90%. You could do that. I am not opposed to making it so that these things are more easily modified. I just don't want them to be too easily modified, because then how can we really argue that a person is following the correct OpenEEmeter model as far as regulatory for regulatory reasons? I mean,
Can I say something as a follow-up?
of course.
So there are two aspects here. One is to get a result, and the other option is to get a compliance result. I'm thinking that for a research purposes or some other kind of usage, you should open it for like any outcome out of this modeling result. If someone wanted to, for example, have a weak model, and this is right now, this is one of those options for the machine learning. So get a weak result from this model, let's call it, for example, time of the week and temperature, and use that result for a better kind of modeling for the machine learning. So if you consider that one as an option, someone is not doesn't have any obligations to be compliance result with the Caltrack, just using this model for a weak prediction, and then the outcome comes from another model for a research purposes or any other reason, right? So to me, there should be a difference between the Caltrack compliance and the approach you are using based on the scikit-learn, which is a predict or model.fit.
So are you pushing more for a structure where it would always fit regardless of compliance, and then is Caltrack compliant or not? Would
Yes,
that suit your?
yes, absolutely. Because when you look at the scikit-learn as a whole, there are plenty of model that is just there for a purpose of experience, not for the purpose of getting a result.
Okay. Yeah, I've got no issue with that. We'll, like I said, the discussion between Jason and I is we were already kind of debating between these things. So now if there is some weight on one side of this debate, we'll just go with that. And so yeah, we'll set it so that it will always fit and always predict.
I think that's a good idea. I also wonder about the outputs, and in the outputs, having a table that gets generated that's basically like qualified, not qualified, disqualification reason, if that is relevant for any particular meter. So you'd get the results, but you'd have a table that gets generated that says this meter was flagged as running into one of the compliance criteria, and it was this specific issue that came up, something like that. Just that might be more complicated than I'm making it sound, but that'd be something to consider as well.
That's what we're already planning on doing. We keep track of all disqualification criteria, not just the first one that it doesn't pass.
Yeah, got it. Awesome. Okay, cool. Thanks for the feedback, everyone.
All right. And then while we were going through this, we were having to do it with a fine-tooth comb. We found some sufficiency requirements that we don't really agree with anymore. So we're proposing some new sufficiency changes. The first is that there is a requirement that the daily data cannot have negative values, which to me does not make any sense, as if you have an overproducing solar panel array, you could have a negative value for the entire year, or it would be even more likely to be for a very specific day. The second change that I want to make, which I think addresses what the prior one was trying to do, is to add the requirement that non-electric meters cannot have negative values. So how do we want to go about this? Do we want to go with a proposal and a second and a vote, or do we just want to go with nobody has any complaints, we'll just pass this forward?
We do see, just for what it's worth, we've looked at a lot of meter data over here, and we have seen examples of meters that have annual negative consumption. It's not entirely crazy to have that. So these are like real world meters that just have large solar arrays on their rooftops. It's not like a generation facility or anything like that. So the test is kind of a no-brainer, but wanted to, kind of speak now or forever hold your peace kind of thing on this, if folks disagree.
All right.
I do, Travis,
Oh,
have
did you
a
have some-
very large compost pile in my backyard, and I am collecting the natural gas and sending it back to the utility. So there are days when I have negative consumption on the gas side. Just kidding, of course.
All right, so we'll go ahead and make these changes. They will be within the data class of OpenEEmeter 4.0, which is where all of these requirements are going to live going on in the future. We will also make sure that these requirements live in a document within the repository of OpenEEmeter 4.0. All right. And with that, I think we are ready to move on. I'm going to pass the baton to Armin to talk about the hourly model.
Okay, let me see how I can share my screen. Here. Okay, for some reason, I don't know why I can't share my screen in Google Meet. Would you please share your screen, Travis? I just,
Give me just a second. I need to pull it back up.
thank you. Okay, can you go to the next slide? Okay, so let's have a quick recap from the last meeting that we had because it's been a long time. We haven't talked about these things. So the first thing, PNRMSE and CBRMSE. If you remember, PNRMSE was root mean square error divided by a range, which was the interquartile range, Q3 minus Q1. And CBRMSE was the RMSE divided by mean value of the meter data that we have. Sometimes that CBRMSE was misleading because specifically for the solar data, as Travis mentioned, we can have negative values or very close to zero values, and these are the CBRMSE can go crazy. And that's why PNRMSE is doing a better job specifically for solar customers, but it both works for solar and non-solar meters. And at the end of the day, they are highly correlated for most of the time. So from now on, instead of CBRMSE, we're going to analyze and evaluate our models based on PNRMSE. And we show a couple of early results from elastic nets with different hyperparameters that we tuned manually. And we saw the elastic net is doing a better job compared to the current hourly model. And these models have been evaluated by test error, both on solar and non-solar data. And we saw the impact of solar irradiance data on model performance, more specifically on solar customers, and again, more specifically on cloudy days. Can you go to the next slide, please? Okay, so today we're going to talk about different topics. The first one is a huge run and comprehensive analysis of elastic nets with almost 2,000 scenarios. We're changing inputs, durations, lags, which I'll explain it in the next slide. And after that, we analyze multiple models more in this sklearn library, and basically compared the results of those models to the elasticnet model that we had. And at the end of the presentation, I'm going to show different type of results. The first result would be the different model performance, the selected version of all of those models that I explained above. And we'll show out of those scenarios that we explored for the elasticnet, which one were the best ones. And at the end of it, we're going to show a couple of plots, which I think they're the most important part of this presentation in the hourly section. And they're basically, we're talking about the population result in different point of view of how the elasticnet model is performing compared to the current hourly model. Travis, thank you. Okay, so elasticnet scenarios. We had a huge run for the elasticnet. We wanted to explore what are the best options for us to analyze with elasticnet model. The first, the main element of that model was how we can set up the input data. What are the input data that we can have? It could be temperature, solar data, which is GHI, humidity, and all sort of weather data. And in each scenario, we pretty much explored and combined these weather features. And um, another important variable for us in the ElasticNet are basically hyperparameters of the model itself. We have basically two hyperparameter, alpha and L1 ratio, which basically they are changing the contribution of the regularization factors that we have. Basically restrict the whole model to not overfit, and then so we can have a well-fit model. And another idea came up in a couple of previous meetings that we had was, should we focus on more cloudy hours, or basically penalize the model in a way that we have more focus towards those cloudy hours, and we want to have a better prediction for those hours. And for all of these combination of these scenarios, input data, what duration we want to use. We wanted to lag it for a day, for 2 days, and all of this combination. We did it for 2 segments of the data, and all of them are residential meters. One segment was 1500 solar meters, and the other segment was 1500 non-solar meters. So basically, in each scenario, we run all of the models, ElasticNet model, train the model for 1500 meters in each segment. And basically, we evaluate the models based on the tester PNRMSE. After that, after we got the results for those big run that we had, we explored other models, which are common regression models, such as extra tree regressors, which we talked about it before a little bit, XGBoost, AdaBoost, neural net. But here we just use shallow neural net or a multi-layer perceptrons, and they are not deep learning models for obvious reasons that we talked about before. And the other model we chose was support vector machine. Support vector regressor. Basically, we collect different models from different segments of regression models, from linear to nonlinear. Some of them are based on decision trees, and one of them neural net, and the other one is SVR. So these are the type of models that we explore. Travis?
We have a question.
Oh, we have a question.
Of, how do we know which households are solar and non-solar? Existence of negative values? Question mark.
So basically, I get the data with the label if and they are solar or non-solar. So I think that's one of the criteria. The other one is if we label the data with the rate, the pay NEM. I think, Adam, if you can.
Yeah, oftentimes, well, with solar PV, there are almost always interconnection processes that the customer has to go through, and the utility needs to be part of that. So utilities usually know and keep track of which customers have solar, just as a metadata field. At Recurve, we have grown to be distrustful of utility metadata because we've just seen a lot of it be fairly unreliable. Although there are many exceptions to that. So we also scan for negative meter readings. And if there are, the presence of negative meter readings, or if the customer's been identified by the utility as, having solar PV, then we'll flag that customer as having solar PV. Having said that, I have seen at least one data set that was mostly larger commercial customers, and the utility I'll just tell you who they were. It was Ameren, Illinois. And they did not keep track of which customers were solar customers. And most customers in this data set were large commercial customers. And if they had solar PV, they never went negative. They never generated more than they were consuming. So, I've seen an exception to that, but it's pretty rare from what I've seen, although others here may have different experiences, and feel free to speak up. So I think usually we will have a sense of who is a solar customer and who's not based on those flags.
And I just volunteer one other observation. I don't know how common this is, or whether it represents any kind of issue for training the models and doing this like validation test that we're in the middle of. But it does sometimes also happen that an account is flagged as having solar, but the solar system isn't working, it hasn't been for a long time, or the customer removes it or something like that. So there's also false positives sometimes in those flags. I mean, if you're just kicking them all out of the system, then false positives are very little cost, because it's a minority of a minority. But if we're trying to train on like actual solar from known solar, it is a little annoying to try to figure out if there's false positives in your set. But hopefully those aren't too common for all of our sakes.
Yeah, good point.
Biggest
And
problem.
oh, sorry, just really quick. There's also some customers that have distributed wind or geothermal. We had one customer a while back that just had 1,000 hamsters running on wheels, and they were frequently producing more than they were consuming. So with that being said, I think you never quite know whether a customer is specifically solar, but the vast majority of customers with distributed energy on their generation or distributed generation is solar PV. Travis, sorry.
The biggest problem that I think we have is that we're talking about 3 years of data in order to do our rolling test train, and so we don't have a date of installation of these solar PV systems, which can often lead to problems where part of the year is being there is no solar system, and then part of the year there is a PV system, and this wreaks havoc with our models. I expect that in the future we are likely to add sufficiency requirements related to this for the hourly models.
Yeah, that's basically more like a pre-processing concern rather than modeling. And if there's anything that we can do over there, it's either with solar detection, as I just add a new project, Adam, solar detection, and solar disaggregation, which is another different project. Good, Travis. Thank you. Yes, Thomas.
You guys might just offer a thought there on a couple of those things. I think one is that installation dates and such are often available from manufacturers, and certainly a number of them have within their own APIs, a interconnection date or commissioned on date that you can retrieve. But then also, a lot of this data is also available directly from those manufacturer APIs as well. That you can get typically many of them up to about 2 years worth of historical data that you can sort of directly incorporate. And a lot of that is, some of it is, I mean, you can either get it from the device's internal meter, or some of them also have external sort of site level revenue grade meters as well that they'll report to their APIs.
Yeah, the requirement for that, I think, would be to have the connection or access to their data, or because the only thing that we can get, I think, Adam, correct me if I'm wrong, we get it from utility data, and I don't think we have a connection to the company or any sort of third party that they install the PVs.
Yeah, I think Thomas's point is a good one. I mean, if you are working with a data set where you know, the manufacturer will allow you to use their API or has the data available and they're part of the project where you can, you know, you can ask them for that data. Absolutely. That is probably the most reliable data source you can come by. I think you don't necessarily always have that available to you, but it's a very good point. I mean, look, we're all out there in the real world, like in the wild, trying to conjure data from wherever we can get it. And if you can get data in a reliable way from a manufacturer, that's great.
Yeah, that would be great if we have the data for all of the meters, but even if you don't, even we have for a subset of meters, that would be a good test or evaluation data set to have a solar detection model. Again, before the actual modeling. So that would be a data pre-processing. Again, no problem. Thank you. Okay, so let's jump into the results. The first result that I want to talk about is the model performance. These are basically the best of the best, and these are not all of the models and all of the hyperparameter tuning and tuned model. And I can say during the previous 2 months, I trained more than 1,000 models with different hyperparameters. So these are basically the selection of them. And the first row that we can see is the person test error improvement. And by error here, we mean P and RMSE for the whole test set that we had. If you remember that we had all of that cross-validation, 3 years rolling, and we were talking about all of the test data sets and for all of the meters that we explored. So ElasticNet and this is for solar meters specifically in this table. So ElasticNet has almost 3.4% improvement in the PVRMSE, PNRMSE. And the neural net is again a shallow neural net. It's not a deep neural net. It has 2.75, XGBoost as a little bit lower, and SVR 1.26. And but these are not just the only metric that we wanted to look at. We want to look at the computational time, and the computational time we're talking about here is basically seconds per 250 meters. Why 250 meters? Because we batched our data to 250 meters at a time, so we can have a easier calculation time with the memory and all of those stuff in the virtual machine. So ElasticNet has the lowest computational time. Realistically, it's a linear regression with a couple of regularization factors. So it's fast. We expect it to be fast. Neural net was a little bit slower. XGBoost was surprisingly slow, to be honest. I thought it's going to be way faster, and I tried different setups. If you bring down a couple of hyperparameters, the performance would be worse in terms of error metrics. But if you add more depth to it or other hyperparameters, when you change it, the timing goes up not linearly, so it's not good. And SVR was the slowest with and without kernels. So in general, I was disappointed with SVR. I thought it's going to do a better job. And the okay, I can't see the name, but there's someone wants to ask a question.
Info account.
Yeah, it's my info account. This is Steve Cromer. Hi, everybody, and hi, Armin. I apologize. I had to jump on another call for a second, but going back to your comment about the predicted normalized RMSE versus the CV RMSE. I teach this stuff for a living, and I put a hell of a lot of emphasis into teaching what people. I say the one statistic you need to know if you're an entry-level person in M&V is the CV RMSE. So I'm a little concerned that I now have to either adapt my materials or what's behind that, and how does that all fit together, I guess.
Travis,
So
you want to jump on that one?
Yeah, Travis.
yeah,
was
and
ready.
we run into issues with using CVRMSE when we're talking about solar meters. The reason for that is because if you think about I'm going to do air quotes here, well-designed solar PV system, then for most houses, that means that they are trying to account for their entire usage through solar means. So if we're now going to divide the error metrics RMSE by their average usage, we're by definition dividing it by a very small number, which means that this number, the CVRMSE, is going to blow up. But in reality, its RMSE is not going to blow up in the same way. So this is an issue that we were, I don't think we have the slides immediately available to us, but basically we ran into a lot of issues with using CVRMSE. So what we decided to do is, well, the issue is that denominator. So we're going to change what that denominator is, and we're going to ensure that one, it is positive, and two, that its value does not become very, very small. The way that we found was best to do this was to look at quantiles. Now, I looked at a bunch of different quantiles, so like 95% quantile minus the 5% quantile, all sorts of combinations. And I found that the one that is best correlated with CVRMSE is to use the interquartile range, which is the 75% quantile minus the 25% quantile. What this does is we are now ensuring that that value is always positive, and despite the fact that a solar meter might be producing almost equal to its consumption, its range of values is still going to be pretty consistent with another meter that is going to also have its own range of values. So when we divide those things out, then we make sure that we're able to compare just like we are with CVRMSE between meters.
I hear you, and that all that I'm sure I could be easily convinced, if I'm not already, that it's a good reason to do it. I guess just from the perspective of a more generalist in the industry, how do you see communicating that, or do you think it's going to cause confusion? Is that a worry at all? Or I see Adam nodding his head. So
yeah, yeah. Anytime you monkey with some of these parameters that we've all like grown to rely on, yeah, there's concern over that, without a doubt. And I think what we're likely going to do, Steve, is at least for the model outputs, we'll track both CVRMSE and PNRMSE, but we'll attempt to utilize PNRMSE as the standard metric across all, in order to define things like model fit thresholds and disqualification parameters and things like that. But also make CVRMSE available in the data sets, so that folks can get a gauge of that more like that parameter that they've built their intuition around for so long. I'm one of them, without a doubt. So it's not a decision that we sort of take lightly, and I think we had hours of discussion, and ultimately Ethan suggested that we kind of scan over a lot of the values, and it just happened to be kind of coincidentally that the interquartile range gave the closest correlation with CVRMSE, which was something like 0.6. Yeah, do you have that graph? Something like 0.67. So it's not too far off in the majority of cases, but of course, you get some of these squirrely outliers where it is very different. So there is a bit of a trade-off there.
Okay, and let me just, I totally appreciate it. You said it said music to my ears. Let me say, I actually think it's probably the right way to go, because I think all modeling is going to have a lot more modeling is going to have these problems going forward with PVs, EVs, and all the weird stuff happening on meters. So I think it is the right way. I just wanted to know kind of like how we all collectively nurse the industry into the new world, But
well, I'll tell you how we do it. We make it part of your coursework.
Yeah, exactly. Well,
you make sure to give a quiz around it to all of your students. Like that's the way we get there ultimately.
Great, thanks. Sorry for if you went on with this for hours earlier, but thanks for the explanation. I will
no, it's all good. I'm really glad you're here, Steve, and it's good to
Steve.
Chime in.
Yeah, Steve, let's grab coffee sometime and talk about it.
Sounds good.
Travis, before you go,
all your intuition.
Can you go
about
to
how
slide
this
number
works is-
32?
Yeah, go ahead.
Okay.
Yeah, here. So I was talking about this. If you can see in the CBRMC on the right side, the middle figure, you can see that's the CBRMC for 100 solar customers, and you can see like anomalies on the negatives and even on the right side and the positives, because the average observed value for them is either so close to zero in the positive or negative side. That's why it just blows up in the left and right. And then the same histogram, but I mean same meters, but the PNRMSE for them is on the right figure. As you can see, it's like more close to each other, more reliable to compare these meters errors.
Looks good.
So, sorry, Brian, I cut you off. I wanted Travis to show this.
Yeah,
Where we
while
go.
Travis is pulling up the other slides, I want to say, like, one of the things we've discovered as we get more and more solar customers in our data sets in California is that there are a whole bunch of embedded assumptions that you don't think about as you're doing this analysis, where you're assuming that all energy consumption is positive when you're developing your methodology, and that this sort of falls apart. So we're trying to figure out the right way to deal with it going forward.
Great. Thanks, guys.
Yeah, and the nightmare is when you combine the PV with the batteries. It's pretty much zero, and even PNRMC can be misleading at that specific meter too. So we need to take care of that later. Okay, so we talked about tester improvement for these selected methodologies or models. And we talked about computational time. We can see ElasticNet is doing a good job. And overfitting score, which means what was the PNRMC error for the whole population in the test set divided by the train error set. So ElasticNet is 1.36. So as we can be as close as possible to 1, that would be great. That would be the well fit model. And if this number goes up, which means you're doing a great job in train set, but not as a good job in the test set. So as we can see, XGBoost tends to quickly overfit, and that's pretty much true for most of, not even, maybe all of the decision tree based models. If you tweak them a little bit with the hyperparameters, they can easily overfit. But ElasticNet is doing a good job. As we can compare to the OEM overfitting or the current hourly model that we can see, the score is 1.47. So still ElasticNet is doing a better job in terms of overfitting score, and not just the absolute error by itself. Yes, Mustafa.
I have a little bit of doubt about overfitting a score as you explain it, because there are lots of parameters should be considered there. As you explained, for example, hyperparameter tuning or data leakage between the train and test, or maybe like a cross-validation method. Kind of my question is, how confident are you about the overfitting score for the comparison of these methods?
Yeah. So basically, all of the results comes from a cross-validation scheme. Travis, can you go, sorry for doing that. Can you go to the appendix so we can show the 3 years rolling? Yeah, here. So basically on the right side, you can see the figure, and the figure that you can see is
Hi, Denise. This is Steve Cromer. Thanks for your call. Apologize, I had to attend to another question I just asked on a meeting. I'm available.
Okay. A different meeting. So basically, we have 12 k-fold here in the way we set up our test train model. We have 3 years of data, and we start from the beginning of the first year. And first year would be our train set. The next year would be our test set, and then we shift the months one more time, 1 month, and the first period would be our train period, the first year, and then the next one would be test period. And then we shifted 1 month at a time all the way to so we can cover the whole 3 years. So each one of them is actually a different train tester, and we train the model differently in each basically cross fold, k-fold, and we take the average for all of that. Actually, we have the uncertainty for all of that as well, so we can play. We can actually see the test error uncertainty as well.
I would recommend to do like a test, maybe a practice to figure it out if those numbers are reliable or not. So I was wondering if you can use another k-folding, like for example, grouping, stratified, or repeated, for example, k-fold,
Yeah.
and see if the results remain the same, like the order of the numbers are the same, or you see a different pattern there. And yeah,
So basically, I'm sorry, cutting you off, because we did that.
So let me just give you an example. So
Sure.
from the ASHRAE competition in 2019, what they found out of 3,000 modeling test cases there, the k-fold or training versus the test data set is one of the most important parameter there to get the result. So for example, as simple as just splitting the data set in two, or using cross validations, k-fold, as you mentioned, make a big difference in the outcome. So I would expect the same kind of outcome here when you define that metrics.
Yeah, sure. So basically, before we do that 3 years rolling window type of cross-validation schema, we did that grouping and stratified sampling before within 2 years, and we did it. I think it was like 2 years. So basically, we are cutting the train test inside of a year. Do the group stratified sampling and all of those things, but we switched to this schema because we figured that this is more realistic in terms of comparing the new model error with the OpenEEmeter model, because in that case we didn't have the OpenEEmeter new model each time. So basically we had some sort of data leakage, as you mentioned before. This one, we trained the hourly model for each k-fold one at a time, and then we train our model and then compare them together.
Yeah, I think there are many formulations of cross-validation that can be utilized. And when we worked on the daily model, we had a pretty sophisticated shuffle split cross-validation scheme that we were using. And as you know, and the reason that we were able to do that is that we completely reformulated the daily model as it existed previously for the purpose of that analysis. This time around, it's impractical, really, because the hourly model is much, much more involved to take that approach. Although, you know, we would like to, but we're all working on volunteer hours over here on this project. So we felt like this was a good way to emulate the benefits of test train splitting and to get multiple samples as you would typically in cross-validation. So this is essentially a custom cross-validation algorithm that we've written, and it's not perfect, but I think we're largely getting those benefits. And when I look at the numbers that Arming presented on the model comparison, what I'm seeing is quite a bit of differentiation between the models. You know, it's not like we're making a close call here. There's really substantial differences that we're seeing. So I don't feel like we necessarily need to go a ton further on this in order to make a decision ultimately about which models we progress further in researching and which models we don't. But I'm happy to talk more about that.
So our original reason for switching to this rolling test train was actually to prevent any data leakage, as previously we were pulling days out in the middle of the year, which definitely could result in data leakage. Now, as it stands, the other reason to really criticize what we've currently done is not about data leakage. It would be because that's simply not possible. What you could criticize is that we're not getting an accurate test train simply because things have changed over 3 years. So we basically have to make a compromise somewhere, and we chose that the best compromise that we could make is basically to try to isolate for customers meters which have changed as little as possible over those 3 years, and then to perform this rolling test train split as we've done.
So we're using data from what, 2017 through 2019, right? So we're going pre-COVID.
Yes.
And we've done quite a bit of analysis on pre-COVID data to understand what are the year-over-year changes in energy consumption that we should expect to see from large samples. And it's very, very minimal, fraction of a percent kind of thing. Although it's not nothing. And you'll see some evidence later on that it's indeed not nothing.
Yeah. Let's go back to.
All right.
Yeah.
So just in the interest of time, I'm going to move on from that question. Mustafa, if you still have concerns, please feel free to email me, Armin, Adam, and we can even set up another meeting to talk about it if you'd like.
100%. Okay. So we basically talked about this. Next slide. Okay, this is a really important result out of all that big run we did, big comprehensive analysis for the ElasticNet. So in the non-solar meters, non-solar section data, we find out if we just use the temperature, no other features, without any lag data, so basically 24 hours temperature in the same day, map it with the model to the same day 24 hours without any lag, and without any emphasis on the cloudy hours or anything, we're going to get the best result. And within those scenarios, that ElasticNet with the alpha 0.1 and L1 ratio 0.1, which these are the parameters for the regularization, would be the best choice for us in terms of PN-RMSE improvement compared to the original hourly model that we have, which for the non-solar customers, we have 1.35% improvement in terms of PN-RMSE. Next slide, please. And for the solar meters, we figured that we have to use GHI with the temperature so we can get the best result. And everything else is pretty much the same, which is the good news for the elastic parameters. For the solar and non-solar data, we can see the hyperparameters are the same. We're not going to use any weights on the cloudy hours, no lags. So basically 24 hours data matched to the 24 hours AMI data set. And the population level PN-RMSE improvement is almost 3.4% over the OEEM. And can you go back, Travis, one slide? So basically here we just use temperature. This is the best scenario. But the next scenario after this was when we use temperature and GHI again with the same hyperparameters, which means, and the errors are very close to each other. It's 0.01% difference. So basically, if you want to have a consistent input and model, we can have that at the same time without honestly compromising the error really much. So we can use temperature and GHI with the hyperparameters that you can see for the ElasticNet 0.1 and 0.1. Everything is consistent for solar and non-solar data set. Next. Okay, so far what we have seen, we see different model performances. ElasticNet was doing good. We saw overfitting degrees. Again, ElasticNet was beating other models. As Adam mentioned, it was like a battle between the models. So far, ElasticNet is a winner. Computational time, definitely ElasticNet was the best scenario when we're using the window size inputs. And so as you can see, the error improvement for the solar meters is around 33.5% in PNRMC improvement for the test data set, and 1.5% for the non-solar meters. So these are not that substantial improvements in terms of percent improvement. But if you wanted to have a different point of view of different metrics, we can see if these are this new model, which is the ElasticNet, de-risk the output of the model in many ways, which I will show you in the next few slides. And that can help us to see the impact of the new model in the cloudy days, more specifically for solar customers, and not just the error itself, PNRMC. We can see even this new model is less biased, which I'll explain later. So before we jump into the next 4 slides, which are the most important slides for the hourly model results, I want to introduce again the Cloud Coverage Index, or CCI, which is clear sky GHI minus GHI. What do I mean by that? Clear sky GHI means solar irradiance in a flat surface without any cloud. So whatever we have, we can even calculate it. We don't need to measure it. We can calculate for each location in the world at any given time. And for the GHI, that's actually the measured solar irradiance for that location. So if we have a sunny day without any cloud, this clear sky GHI minus GHI should be 0 for the whole day. And if we have a cloudy day, then the measured GHI is lower than clear sky, so we have more values for the CCI. And we use this in the hours that clear sky GHI is positive, which means we got rid of the 0 values in the beginnings, which means we consider the day time as well. So winter, shorter days, and longer days for summer. Sorry, Travis.
I want to let you know that you've only got 8 minutes left.
Okay, so let's move on to the next slide. So this is the population level results for the non-solar meters. And in the x-axis, we have the CCI, or cloudiness index, which means we start from pretty much sunny days on the left, and as we go to the right, we have more cloudy days. And the y-axis is the PNRMC improvement compared to the OEEM, and this is for the test data set. And as you can see, for the non-solar meters, we have improvement generally around 1%, but the cloudiness index is not that relevant. So that cloudiness, or GHI, doesn't change a lot in the model performance for non-solar customers. Can we go to the next, please? Okay, and this is the same plot, but for the solar meters. As we can see, as the more cloudy days we have, the better the percent improvement of the model. This means that by using solar irradiance data, we can actually help the model to understand the pattern of AMI. As simple as that. Pretty much we can see the trend, use the GHI value, and map the input features to the output feature. That's why we have a higher percent improvement in the cloudy days, which current hourly model doesn't even have a clue of this type of data set. Okay, so that was PNRMSE, or kind of related to the our root mean square error. Now we want to talk about normalized mean bias error. We use this frequently in the daily analysis for the season, if you remember, for the seasonal bias. But this means basically the average bias, which bias is model minus observed value, pure without any absolute value or squared values. And in order to compare these meters by meters, we divide it by, again, that range, inner quartile range, Q3 minus Q1. It looks like a PNRMSE, but basically that shows the mean bias error, a normalized mean bias error. So if this value is positive, we have over prediction, which means the model is over predicting. And if it's negative, when we talk about the negative, the mean values, we have under prediction. So next slide, please. This is the population result for non-solar meters. X-axis is exactly the same. Y-axis, we have NMBE. This is not percent improvement. This is actual value of normalized mean bias error. For the non-solar customers, we can see both of the models are under predicting. And as we go towards the more cloudy days, this is more obvious. And the new model is doing a little bit better job, but it's not that significant. So that's one of the things that we need to look at more in details in the future analysis. But as of now, for the non-solar meters, we have under prediction for both of them. But for the solar meters, Travis, that was a little bit of lag. Okay, so but for the solar meters, as we can see, this normalized mean bias error is so close to zero, and no matter what, from sunny days all the way to cloudy days for the new model, which is the elastic net. And just have in mind that we want the best model would have zero bias. But right now we have a little bit of over prediction in the sunny days for the elastic net, but less, but a little bit under prediction on cloudy days. But as we can see for the current hourly model, we have a huge under prediction for more cloudy days, which makes sense because we're training the model for more in the baseline with more sunny days, and we're not aware of solar irradiance data anyway. So the model tries to balance between the over prediction and under prediction throughout the whole year. That's why for the cloudy days we have higher under prediction, and for the sunny days we have more over prediction because of the size of the PV that it considers inside of the model.
So Elaine, the reason why non-solar meters would show poorer bias during cloudy times is because when the original model is being trained on the entire year, then that means that it's having to be pulled down on. I have to make sure I'm getting this right. During sunny times, the model is going to be pulled up, and during cloudy times, it's going to be pulled down, which means that then when you're evaluating that same model, you're now evaluating it on a time period. For example, let's say last October 1st was cloudy, and this October 1st is very sunny. You're going to get very different results based on that. And we can come back to that if you still have more questions. I'm just trying to make sure that we get done on time.
Yeah, and for the future analysis, we really want to focus on overfitting issues. The overfitting scores, even for the current elasticnet, is not as good as me and Travis expected to be. I want to dive into load chip analysis for different seasonal bias, seasonal load shapes, to see what actually we're doing in the population level. Ensemble models, do we want to go ahead and maybe have separate, for example, one of the ensemble, have separate models for different months and add them together, like what we have in the OpenEEmeter, or have different models output votes or average them for the better AMI prediction. And at the end of it, we want to have a comparison between the current hourly model computational time with the selected model.
So upshot is we've tested between the last time we all got together and today, we've tested several different models, and we're essentially keeping track of what is the error metric that we're using, that we're seeing in this case, PNRMSE. How does it compare to the existing Caltrack 2.0 model? What are we seeing in terms of the degree of the models being overfit? And what is the computational cost of these models? And across the board, the elastic net seems to be outperforming any of the other categories of models that we've studied so far. So we have more work to do before I think we totally settle on an elastic net approach, but I do think we've gone through a pretty rigorous process at this point of trying to ascertain what the best modeling strategies would be in a general sense. And we'll probably start circling the wagons and working a little bit more on refining as opposed to like broader based experimentation going forward. So it's good. It's nice to get to this point in the group. And hopefully, we'll be on the downslope from here, which is great. So really appreciate everybody's input today, by the way. And Travis, I'll kick it back to you.
All right. I'm just going to address what Mustafa said so that I can stop typing. Yes, we are interested in doing LSTMs and neural nets as well as transformers and so forth. What we don't know right now is if we want to just kind of put a bookend on the current research and get that pushed out as 5.0, because we're really wanting to make this more iterative and less like we're only going to put out one big release that is almost perfect once a year. We really want to make it so that the newest models can be out more frequently.
Real quick, I add something. We use LSTM for the solar disaggregation project that we had before. It's I can say compared to the elasticnet, it's a little bit overkill and needs more computational power, like GPUs. Maybe in the future we can add that as a feature.
All right. And as Adam said, thank you all for the great questions and for the feedback. We will certainly always take that into consideration for next time, as well as to help us lead where this research goes. So we really can't do this without you. And again, thank you all so much.
Good work. Thanks, guys.
Thanks.
All right. Till next time.
Thanks, everybody.
Yeah.
See ya.